I want you to just close your eyes for a second and picture the absolute torrent of data flowing across the planet right now. It's
All right.
not just, you streaming a movie. It's this intense, constant conversation between huge AI models on different continents. It's high-frequency trading algorithms fighting over
It
milliseconds.
sounds chaotic, less like a flow and more like a frantic digital drag race.
Exactly, a drag race. And everyone wants to go faster, but here's the thing we always hear. The internet runs at the speed of light.
Yeah, which should be instantaneous, right?
That's the lie we've all been telling ourselves, because for almost 50 years there has been this hidden bottleneck, a hidden speed bump. Even though our data is literally light pulses in a fiber optic cable, the glass itself, the silica, it acts like digital molasses.
Digital masses, I like that. So wait, how slow are we actually talking here?
We're talking about a really significant lag. The light going through that solid glass fiber gets slowed down to roughly 2/3 of its speed in a vacuum. Yeah. And if you do the math on that, it means the entire backbone of our digital world, everything, has a 45% speed penalty just baked right into the wire.
45%. Whoa, that's not a small number.
Not at all.
So you're telling me every single global transaction, every Zoom call, every remote surgery is happening almost half as slow as it could be.
Yeah.
That's like a gigantic, unavoidable time tax on everything.
It's the immovable object, the invisible wall that engineers and, physicists have been slamming their heads against for more than 4 decades.
4 decades.
For nearly 50 years, they were stuck. They hit this physical, unbreakable limit that's just imposed by the glass itself. It limited how fast the data could go, and also how much of the signal you lost along the way.
So every time we laid a new cable under the ocean or through a city, we were just building in that same time penalty. The glass itself is the villain of this story.
Precisely, and that's what makes this moment so incredible. This deep dive is about the twin scientific adventures that finally and somehow simultaneously just shattered those limits.
Okay, twin adventures.
Yep. We are looking at 2 separate but equally critical breakthroughs that are basically defining the future of the internet's backbone. One gives us this unprecedented speed by, getting rid of the glass. And the other gives us this massive, massive capacity by packing in more digital lanes than we ever thought possible.
Wow. Okay, let's unpack this. How in the world did they pull off this dual revolution?
All right, so before we get to the heroes, we really have to appreciate the villain here. The physics and the history that made this problem so hard. I mean, the whole quest for faster long-distance communication is what created our modern world.
Yeah, it's easy to forget that. I mean, for most of history, communication was literally as fast as a horse could run.
Exactly. We went from, fire beacons on hills to those mechanical optical telegraphs in the Napoleonic Wars, and then the huge leap, the electric telegraph, that first transatlantic cable in the 1850s.
That was the game changer, sending electrical signals under entire ocean.
And then you fast forward about 120 years, and you get the real revolution. We shift from those old copper coaxial cables to optical fiber in the 1970s, and the leap in sheer data was just staggering. We went from signals measured in kilohertz to light signals measured in terahertz.
That's like going from a garden hose to a tidal wave.
1,000,000 times more, easily. But even with that huge jump, 2 goals stayed the same, and they became the new frontier. First, send more information. We call that capacity.
Right.
And second, reduce how much signal power you lose along the way. That's attenuation.
Attenuation, measured in decibels per kilometer, or dB per kilometer. The lower that number, the better, right? It's all about efficiency.
It's all about efficiency. And that matters because lower loss, lower attenuation means the signal travels much, much further before you need to regenerate it, before you need one of those expensive power-sucking repeater stations.
And if you're laying a cable under the Atlantic, every single one of those repeaters you can skip saves you, what, millions of dollars?
Millions. Capital, construction, maintenance. So the goal is just dead simple. Make the distance between repeaters as long as possible. That's the money behind the science.
Okay.
But this is where the story just grinds to a halt. For 40 years, despite billions of dollars in research since the 70s, the minimum attenuation you could get from those silica glass fibers just danned. It didn't change. The physical goalpost was stuck, fixed at around 0.14 dB per kilometer.
Wait a second. That's baffling. In a field like this that moves so fast, you're telling me for 4 decades, with all the PhDs at every major tech company and university, they couldn't get below that 0.14 number.
They couldn't. It must have been so frustrating.
I can't even imagine.
The work became this agonizing process of tiny optimizations, trying to get reductions of millidecibels, purifying the glass a tiny bit more, tweaking the wavelengths by a few nanometers.
And nothing worked.
Nothing fundamentally broke the barrier. It just proved they were right up against a hard physical limit of the material itself. It was the glass ceiling.
So if the engineers were doing everything they could, what was it about the physics of glass that makes it so stubbornly lossy? Why isn't it perfectly clear?
It's a perfect trap, really. It comes down to two different loss mechanisms that cross over right at the ideal wavelength for transmission, which is about 50 nanometers.
Okay.
The first one, which is the big problem at shorter wavelengths, is called Rayleigh scattering.
All right, hit me with the analogy. What is scattering in simple terms?
Okay, so think of the light signal not as the smooth wave, but like a tiny rally car trying to race down a glass hallway.
Got it.
Rayleigh scattering is caused by these microscopic little fluctuations in the density of the glass. You can think of them as invisible potholes. They're these tiny frozen-in imperfections from when the glass was made.
So even though the glass looks perfectly smooth to us, to the light, it's actually a really rough road.
Yeah.
Exactly. A super rough road. And when the light hits one of those potholes, it scatters. It goes in all directions. Some of it keeps going forward, but a huge amount of that light's energy just gets bounced out of the core and is lost forever.
Wow.
And this is not a small thing. Rayleigh scattering is responsible for about 96% of all the loss in standard fiber.
96%.
Right.
So the problem is literally these tiny impurities that we just can't engineer out of the glass.
Can't make it perfectly uniform. And then on the other side of the spectrum, at longer wavelengths, you hit the second problem, material absorption.
Okay.
This is just the silica itself. The glass intrinsically absorbs light at those infrared frequencies. It basically just eats the light's energy, heats up a tiny bit, and the signal disappears.
So at short wavelengths, the light bounces off the rough road. That's Rayleigh scattering.
Yep.
And at long wavelengths, the road itself just eats the car. That's material absorption.
That is the trap. Those two loss curves cross right at 15 nanometers, and that creates the absolute non-negotiable floor for silica, that stubborn 0.14 dB per kilometer.
That is a beautifully tragic piece of physics.
Isn't it? If you go shorter, scattering gets way worse. You go longer, absorption gets way worse. You're stuck.
Wow.
And that brings us to the second huge problem they had to solve, the capacity constraint. I mean, data traffic is just exploding. Projections are what, almost 5 zettabytes a year by 2026?
Which is an insane number.
It is. And the old way to handle that was just to, add more pipes, put more and more individual fibers into one big cable.
The classic engineering solution.
Yeah.
If one lane is full, build another one.
Right. But
Mhm.
that runs into a huge scaling problem, especially for those subsea cables. If you want to add more fibers, you have to make the whole cable wider.
And that means more material, more cost, more weight. And I imagine trying to lay a much thicker, heavier cable on the ocean floor is a nightmare.
An engineering and financial nightmare. So you can't just keep making the cables fatter. They needed a way to get way more density without changing that standard, super thin 0.125 millimeter diameter of the fiber itself.
So two massive separate problems. Speed and loss are stuck because of the glass material,
Right.
and capacity is stuck because of the cable's physical size.
Exactly. And that led to what researchers now call the great bifurcation of fiber design. The search for a solution just split down two completely different paths.
This is where it gets good. So tell me about the first quest, the one that was all about raw speed and breaking that 40-year-old record.
That is quest number 1, the hollow highway. It's based on hollow core fiber, or HCF, and the idea is just, it's so radical, you completely abandon the solid glass core. You just take it out and replace it with air.
Just air.
Just air, because if the light is traveling through air, all those physical limits of silica, the Rayleigh scattering, the absorption, they just vanish.
Okay, my history alarm is going off again. If the idea is that simple, why didn't somebody do this, 50 years ago? I mean, surely someone tried to shine a light down a hollow tube.
Well, they did. Bell Labs tried it way back in the 1950s with hollow waveguides, but they just leaked energy everywhere. And then in the 90s and 2000s, people tried again with different types of HCF, but they just could not get the loss below 1 dB per kilometer. The light just wouldn't stay inside the air core.
Why did it leak? I mean, if you shine a light down a pipe, Shouldn't it just bounce off the walls?
You'd think so, but at the scale of light waves, it's not that simple.
Hmm.
For the light to be perfectly contained, the walls have to act like perfect mirrors. And with the early designs, when the light touched the glass walls, even for a split second, it would just leak out.
Okay.
And that's why this new design is the hero of our story. It's called double-nested, anti-resonant nodeless fiber.
DNANF. DNNF. Okay, that sounds like something out of a spy movie. What does it do that stops the leak?
It's this incredible microengineering. It basically turns the glass from being the road into being the guardrails. The structure has a core of air that's the fast lane, but it's surrounded by these meticulously engineered concentric glass tubes that are only microns thick.
Concentric tubes.
Okay.
Let's go back to the analogy engine. The rally car in the glass hallway.
Right, the rough road.
In DNANF, the car is now racing through a perfectly smooth air tunnel. The light barely even touches the walls. But those walls, these ultra-thin glass tubes, they're the key. They're designed to act as anti-resonant mirrors.
Anti-resonant mirror.
Yeah, imagine the thin glass tubes are like multiple layers of perfectly spaced plastic wrap. When our light signal tries to escape into the glass, the specific thickness and spacing of those layers is mathematically designed to basically cancel out that wave and reflect it right back into the air core. It's a structural trap.
So nested means you have multiple layers of glass, and anti-resonant means they're tuned to reject the light you want to keep.
That is so clever. You're minimizing the time the light spends in the glass to basically zero.
Almost zero. And the second you do that, the whole game changes. We've just eliminated the thing that caused 96% of the loss Rayleigh scattering by literally removing the core.
Right.
So the fight completely shifts to a whole new set of problems.
If the light's barely touching the glass, what's even left to cause any loss?
Okay, so two new villains emerge. The first is called microbend loss. This happens when the fiber gets bent, even a tiny bit. Because the light is so dependent on that perfect geometry of the walls, even a microscopic little bend, like from the coating or some external pressure, causes the light to hit the structure wrong and leak out.
Huh.
The second is surface scattering loss. This comes from tiny imperfections on the inner surface of those thin glass tubes. Any little speck of dust or roughness on that inside wall and the light scatters.
So we basically traded one set of physics problems, density flaws in solid glass, for a new, equally brutal set of engineering problems. Now you're fighting microscopic bends and surface roughness. That's an amazing shift.
It is. So, okay, HCF solves speed and loss. But we still need that raw, insane capacity. And that brings us to quest number 2, the multi-lane freeway.
The density challenge. How do you cram way more data into that same standard fiber diameter?
The answer is multi-core fiber, or MCF. So instead of one light-guiding core, you put multiple cores, maybe 4 or 7 or even 19 all, inside that same standard fiber.
Like taking a single-lane road and just painting 3 new lanes on it without making the road any wider.
That's a perfect analogy. But it creates this massive, unavoidable problem, crosstalk.
Interference.
Yep. If you pack all those cores that close together, the light signals from one core are guaranteed to leak into the others. It's just physics. You can't avoid it.
And usually crosstalk is the enemy, right?
Yeah.
You want to avoid it at all costs.
That's the old way of thinking. The new paradigm is completely wild. Instead of fighting the leakage, the designers just accepted it. They embraced it. They created what's called coupled MCF.
They embraced the leakage.
Right.
That seems completely backwards. You're intentionally letting the signal get scrambled.
You are. You're trading a clean signal for massive spatial density. You can pack way more channels in. So by the time the light gets to the other end of the cable, it's a complete mess. All the signals are jumbled up across all the cores. The receiver just gets noise.
So do you. How do you fix that?
You unscramble it with a ton of computational power. They use this advanced signal processing called MIMO, multi-input, multi-output.
Okay.
Think of MIMO like this. You're at a party, and 19 people are all shouting different things at you at the same time.
Right. Just noise.
Just noise. But what if you had special headphones with a supercomputer inside? That computer could analyze the tiny differences in timing and frequency for each voice and mathematically separate every single conversation perfectly.
That's a great analogy. So the physical cable is intentionally flawed to get more density, and then you use powerful electronics to fix the mess at the end. But that MIMO processing sounds incredibly complex and power hungry. Is the capacity gain really worth all that power consumption?
And that is the billion-dollar question. You nailed it. The complexity of that processing determines the cost and the power draw of the whole system. The R&D focus has shifted from making purer glass to making those MIMO transceivers more energy efficient.
So you've moved the problem out of the physical cable and into the server rack at the data center.
Exactly. And to squeeze even more in, they started combining MCF with another trick, multi-mode fiber. So now you don't just have multiple cores, you have multiple paths for light within each core.
So it's a multi-lane highway, and each lane has its own sublanes.
You got it. Researchers at NTT and Hokkaido University came up with a design that gets 21 signal couplings in a fiber that only has 7 physical cores. It's a way to get a huge channel count without making the MIMO processing completely impossible.
That is fascinating. So we have our two champions, HCS, the speed demon, fighting physics with structure, and MCF, the heavyweight, fighting crosstalk with massive digital muscle.
And these two quests, they paid off in a huge way. They delivered these simultaneous world record results that just prove we're in a new era for fiber.
All right, let's start with the big one, the one that broke the 4-decade stagnation.
Yeah.
Did they actually get below that 0.14 dB per kilometer glass ceiling?
They absolutely shattered it. Attenuation defeated. The new floor is now 0.091 dB per kilometer.
Wow.
A team from Luminicity, backed by Microclock, using that DNNF holocore design, measured a record low loss of 0.091 at that standard 1550 nanometer wavelengths.
0.091. That's a 35% reduction in loss compared to the absolute physical limit of glass. After 40 years of being stuck, they didn't just inch past the record, they blew it away.
It's a true paradigm shift. Researchers are calling it one of the most noteworthy improvements in this tech in the last 40 years. And think what that means for the business side. A 35% drop in loss means you can potentially skip 1 out of every 3, or even 2 out of every 3 amplifier sites on a long-haul network.
Skipping repeaters saves an insane amount of money. Power, cooling, maintenance. For a new transcontinental cable, the return on investment for this it's immediate, and it's huge.
And we haven't even gotten to the main point of HCF, which was speed.
Right.
The Air Core delivered a consistent 45% increase in transmission speed compared to solid glass. The light is finally moving much, much closer to the ultimate speed of light in a vacuum.
And that 45% speed boost translates directly to a 30% reduction in latency. I mean, for everyone listening, that's 30% less delay on everything. High-frequency traders get their data 30% faster. Cloud services connecting continents shave critical milliseconds off their round-trip time.
And remember that physics trap in silica? How the usable spectrum was really narrow?
Yeah, Rayleigh versus absorption.
HEF blew that wide open. The usable low-loss band in silica was about 26 terahertz wide. The new HCF expands that to a vowed 66 terahertz.
66 terahertz. So you've more than doubled the size of the optical highway just by swapping out the core. That's like finding a whole bunch of new lanes that were always there but were just too bumpy to drive on before.
It's incredible. Plus, the air core reduces something called chromatic dispersion by 7 times. That's where different colors of light travel at slightly different speeds.
And why does that matter?
It means the light pulses show up at the other end cleaner and sharper. That simplifies the digital processing you need to do, which saves a ton of power in the transceiver. It's an efficiency multiplier on top of everything else.
Okay, so that's speed and efficiency. Now what about just raw power? What did the multi-core fiber guys deliver for bulk capacity?
They delivered numbers that used to be pure science fiction. They hit petabit transmission. The lab record, using that really complex 38-core 3-mode fiber, reached an astonishing 22.9 petabits per second.
22.9 petabits. A petabit is 1,000 terabits. I mean, a whole commercial subsea cable today might run a few tens of terabits per second. This is just an unbelievable leap.
And they showed it works over long distances. They hit a new long-haul benchmark of 1.02 petabits per second over 1,800 kilometers.
1 petabit. Over continental distances. That proves the whole architecture. You know, accepting the crosstalk and then fixing it with MIMO is actually viable for real infrastructure.
And then the final test. Could it survive the real world? NTT did a field trial. They got 455 terabits per second over 1,000 kilometers using a 12-core fiber that was installed in a service tunnel and even on overhead lines exposed to wind and rain.
That's the critical step. You have to prove that the digital unscrambling can handle real-world vibrations and temperature changes, not just a quiet lab. 455 terabits stable against the weather. That confirms MCF is ready for prime time.
So we have these two champions. HCF is blindingly fast and super efficient. MCF has this jaw-dropping capacity. The big takeaway for the future of the internet is what they call a bifurcation strategy. You don't choose one or the other. You deploy both of them for different jobs.
Specialized tools for specialized tasks. So where is HCF, the fast one, going to be used?
The HCF market is all about those latency-critical, high-value links, high-frequency trading for sure. But the really big one is hyperscale data centers,
Okay.
especially for AI.
Right.
Microsoft is betting huge on this. They invested heavily in Luminicity, the HCF pioneer, and they are already deploying it.
At scale. This isn't just a pilot project.
Oh, no. Right now, there are 1,200 kilometers of this new fiber actively carrying live traffic for their Azure cloud network. And the plan is to deploy 15,000 kilometers over the next couple of years.
15,000 kilometers.
They want that 45% speed advantage for their AI workloads, which need that near-instant synchronization between data centers. Plus, they get the huge cost savings from needing fewer repeaters.
So HCF is like the Formula One car of the network. Super high performance, premium cost, used for specialized races where time is everything. So where does the workhorse, the MCF, fit in?
The MCF market is all about global scale and just bulk capacity. This is the obvious answer for new subsea cables and the backbones for 5G and 6G in cities. It solves that physical size problem. Why lay a cable with 100 separate fibers when you can use 10 MCF strands that each carry 12 cores?
Right.
You get that massive spatial density, which makes the cost per bit over those huge distances way, way cheaper.
And we're already seeing it being planned for major projects.
Absolutely. Google and NEC are already working to put MCF tech into the new subsea cable system running from Taiwan to the Philippines and then to the US. It's the ultimate scaling solution for the planet's nervous system.
So it sounds like the physics problems are basically solved. But, every solution creates new problems, right? What are the big logistical headaches these new fibers are creating?
The first one is a big one for HCF. It's the measurement dilemma. Because hollow core fiber is so good at guiding light through air, it has extremely low backscatter, about 30 decibels lower than normal fiber.
Okay, what's backscatter?
It's the tiny amount of light that bounces back toward the source when it hits an imperfection. Since HCF has almost no imperfections in its air core, almost no light bounces back.
Wait a minute, don't technicians use that backscatter to check the health of the cable? They send a pulse down and listen for the echo with a tool called an OTDR?
Exactly.
So if there's no echo, the OTDR is basically deaf. How do they find a break in the cable?
They're flying blind with the old tools. The signal is over 1,000 times weaker. So now they have to use new, super amplified OTDRs or much more complex techniques that use frequency and phase analysis to map the fiber. The tech is so good it broke the maintenance tools.
That is a fascinating problem to have.
Yeah.
You need all new gear and training just to maintain the faster cable.
And speaking of maintenance, there's an even bigger physical problem on the horizon for HCF. The future trajectory for this tech suggests the loss could theoretically drop even further, down to an almost perfect 0.018 dB per kilometer.
0.018. That's practically zero loss. How would they even do that?
By using even larger air cores, like 40 or 50 micrometers wide, and thicker, stiffer coatings, the bigger core reduces the light's interaction with the walls even more.
But there's always a trade-off.
There is always a trade-off, and in this case, it's bendability.
There it is. You make it faster, you make it stiffer.
If they build the fiber to get that ultra-low loss, it becomes significantly less flexible. The critical bend radius, the tightest you can bend the cable before light starts leaking out, it increases dramatically.
How dramatically?
We're talking about a jump from a very manageable bend radius of about 4 centimeters, something that fits in a normal splice box, to potentially 16 centimeters.
16 centimeters? That's a dinner plate.
Right.
You can't just coil a cable with that kind of turning radius into a standard box on a telephone pole or snake it through a tight conduit in a data center.
It forces a complete redesign of all the physical hardware along the network path, so the gains in speed have to be weighed against the huge cost and complexity of re-engineering the physical layout of everything. It's not a fiber problem anymore, it's a civil engineering problem.
Wow, okay, so that's the challenge for HCF. What about MCF? Its challenge is all digital, right?
Correct. For MCF, it all comes down to solving the power problem.
Hmm.
Those record-breaking capacity tests need those huge MIMO transceivers, and right now they are computationally heavy and they draw a lot of power.
Right.
The whole R&D focus now is just on reducing the power consumption of that MIMO hardware,
Yeah.
because if your network upgrade saves you money on repairs but then doubles your power bill at the data center, you haven't really won.
So for MCF, the fiber is ready to go, but the digital brain that runs it is the bottleneck. The future of global bandwidth depends on chip designers making those massive computations more efficient.
So what does this all really mean? In just a few years, we've simultaneously solved two problems that held back global communications for decades. We broke the speed limit of glass, and we broke the density limit of cables.
It's a complete shift in thinking. We've gone from trying to make glass more purified that lasted 40 years to designing these complex microstructures and incredibly sophisticated digital systems. The problem isn't material science anymore, it's manufacturing and computation.
And the strategy is this bifurcation. HCF is the premium high-speed option being deployed by cloud giants like Microsoft for their AI. And MCF is the global upgrade path, giving us the massive bandwidth we need for 6G and making subsea cables way more economical.
And if you circle all the way back to that 45% speed increase, that 30% latency reduction from HCF, that's where the implications get really mind-bending. We are fundamentally changing the fabric of global computing.
The synchronization of AI, the functionality of future tech that needs perfect real-time interaction, it all depends on shaving off that last fraction of delay. We're really moving from the digital era to the instant era.
And that's the final thought, isn't it? The physical foundation of the internet just got 45% faster. What global applications have been waiting, just stuck for that final latency floor to drop? How is this going to reshape what's possible when distance itself becomes almost irrelevant?
Fascinating stuff. Thank you for diving deep with us today.
My pleasure. Thanks for listening, and we'll catch you on the next Deep Dive.